Hello, everyone. How is everyone? So I hope you had a good weekend and a good Easter. I know it was a little different than usual, but I hope you still had a nice one. While we're waiting for everyone to get here, does anyone have any questions about the previous stuff that we've gone over? So as I typed a little bit, you're going to need that Wiggers diagram today. So we're going to go over it together, step by step by step. And it can be a little confusing if you don't know what's going on or if you're not too familiar with how graphs and diagrams work. So I hope that you were able to print it out. If you weren't able to print it out, maybe you could pull it up on your phone or at least some other device so that you can see it the whole time while we're going over it and you can take notes. If all else fails, you can just use the PowerPoints that I already have. And if you printed those, they have Wigger's diagrams included in them. But we're going to wait about another minute so that we can give everyone a chance to get here. Can everybody hear me okay? One last thing before we get started. You probably read the email, but I have posted all of these collaborates on YouTube. So for some people, it's a little bit easier to get to YouTube than it is to find the collaborate recordings. So they're not different. They're just the same ones that we've been going over or been using, but it's just another place to find them. Okay, so let's go ahead and get started. So remember we've been talking about the heart, and we talked about the structure of the heart, the chambers, the valves. We talked about the conduction system of the heart. We talked about how the heart muscle cells are linked electrically through those intercalated discs. We talked about the spread of the action potential over the heart. And then we talked about how the contraction follows that action potential. And so today what we're going to do is we're going to talk about all of the events that happen in one beat. And that is called the cardiac cycle. So it's called a cycle because it's a circle. So remember we went over this. We said that it starts with the action potential. Remember the very fastest part of the heart is going to set the pace for the rest of the heart. And the natural pacemaker of the heart is the SA node. And remember, hopefully, that when you talk about the SA node, it depolarizes automatically. Remember one of those properties of the heart is automaticity. So it's automatic all by itself. It does not need any kind of stimulation from the nervous system or anything like that. It's automatic. And then remember, it has this built-in rhythm. So it happens rhythmically. And if you count how many times it happens in a minute, if you don't have any other influences, it's about 100 times a minute, which makes this the fastest part of the heart. And because it's the fastest, and because all the cells are linked electrically, as soon as this begins to go through action potentials, it's going to force all the cells that are attached to it to also go through action potentials. And then we talked about how the heart has this super sort of highway-like system in it. And it starts right here, and it goes down, and then it goes back up. Remember, this is called the conduction system of the heart. And so we have the SA node. It depolarizes. It spreads over the surface of the atria. And then it's picked up by another node. Remember, that is the AV node. And the AV node then picks it up. And then there's the AV bundle, which acts like a little bridge across the connective tissue. Don't forget there's a delay here of about 100 milliseconds So there's a slight delay, and that gives the atria time to contract before the ventricles get going. And then from there, remember, it goes all the way down to the base of the heart, and then turns around and goes back up. So we talked about how the contraction is between depolarization and repolarization. So the contraction of the atria happens right here. And so you can't actually see contraction on the ECG or the EKG, but you can tell where it happens because it happens between here and here. So right there is where contraction is happening of the atria. And then remember the ventricles depolarize. And because of the position of this, they're going to depolarize from the bottom up, which means contraction is also going to happen from the bottom up. So if you look at where they are, here's depolarization. There's the beginning of repolarization. Remember, the contraction happens between these two. So this part is beginning to contract. So right here is where contraction happens for the ventricles. Again, it follows this action potential. And so for the ventricles, the contraction happens in this direction. It happens from the bottom up. Again, you cannot see this on an ECG, but you can see this, that's here. And you can see this, that's here. And so contraction happens between these two. So hopefully everybody remembers that. None of that is new. Anybody have any questions about it? So then it's going to happen all over again. So as soon as all this is over, this is going to happen again. The SA node is going to depolarize. We're going to do this again, this again, this again, and so on. And so if you look at it, it just happens over and over and over again. It's a circle. It's a cycle. And so that's why it's called the cardiac cycle. And so you can pick anywhere you want to start in a circle, but typically we pick right here. So right there is the P wave. That's where the SA node is depolarizing. And so we're going to get the P wave. Right here is QRS. And so remember, the atria are going to repolarize, the ventricles are going to depolarize. And then if we come around here, right here is the T wave. And then there's this sort of pause, and then it happens all over again. So when we look at it, again, it's a circle. So P, QRS, and T. P, QRS, T. P, QRS, T. And remember, we said that when you look at this ECG, remember, it looks a little bit like this, and I'm going to be able to draw it very well with a mouse. But anyway, it looks a little bit like this. Remember, we said that if you count how many of those are in 1 minute, that's going to be the heart rate. Everybody remember all that? So if we do that, if we count how many there are in 1 minute, that's going to be the heart rate. Well, typically, when you count how many times it goes around, how many times it beats, how many whatever, in 1 minute, a typical average heart rate is 75 beats a minute. A typical average heart rate, that's across all people, all genders, all ages, it's 75 beats per minute. Well, if you think about it, if it's beating 75 beats per minute, if we take and we divide that into 1 minute, you can figure out that each beat takes 0.8 seconds. So in other words, this cycle that we were just looking at all the way around and then starts again, that's 1 beat, and each beat takes 0.8 seconds. Well, another way to say 0.8 seconds is to say 800 milliseconds. So one cycle, one beat, takes 800 milliseconds if your heart rate is 75. Everybody got that? Does everybody understand how it works? So what if your heart rate was 60? So my heart rate is not 75. I just took it and it's 60. So how long does each beat last if my heart rate is 60? Well, we're going to do the same thing. We're going to take the heart rate and we're going to divide it into 60. 60 into 60 is what? It's 1. So that means that each beat is taking 1 second. Or another way to say that would be 1,000 milliseconds. But what if I start exercising and my heart rate goes up to, I don't know, let's say 120? If I look at 120, what is, now remember, I'm going to divide into 60 to figure out how long each beat is lasting. Well, if I divide 120 into 60, I only get a half. I get a half a second. That means that each beat is not taking 0.8, not taking 1, it's taking a half, which is just 500 milliseconds. So look, as your heart rate goes up, the amount of time for each beat goes down. Does that make sense to everyone? Well, the biggest effect from that is that it's not the P wave or the QRS or the T. It's not that. It's this little period of time between. In other words, it's the time when the heart is filling up. It's the fill time. So the faster your heart is beating, the less time there is for it to fill up. If you look at one person's heart rate, it looks like that, but look at this one. It's the same here, but the next one starts right here. Starts right here. And so look, this is the fill time here, but this is the fill time here. Try now. Is that better, Jenny? Is anybody else having problems with the audio? Jenny, can you hear me? Don't forget to make sure your speakers are on. Okay, so does that make sense? So look again, one more time, since she didn't have audio. So if I look at this person's ECG, it looks like this, and there's this pause, and then we have this, and then here's this person's ECG, and then we have this pause, and then here it is, and so on. Well, look, this time right here, this time between ECGs, that's the fill time. That's how the time when the heart is filling up with blood. So look how much time this person has. Let's say their heart rate is 60. Look, they've got a lot of fill time. Does that make sense to everyone? But if I look at this person here, so this is their ECG. How much fill time does this person have? More fill time or less fill time? There's the fill time right there. There's the fill time. There's the fill time. So are they going to have more fill time or less fill time? Less, much less. Well, what does that mean? If you have less fill time, does that mean there's more blood in the heart or less blood in the heart? Means less. And if there's less blood in the heart, that means there's less blood to pump. Does that make sense to everyone? So as your heart rate increases, fill time decreases. And if you have less fill time, you have less blood to pump. So let me ask you a question. Do you think then that your heart rate could be so fast, your heart rate is going so fast that there's no fill time at all? In other words, there's no time for the heart to fill up with blood. The answer to that is yes. But think about this. If there's no fill time, there's no blood, is your heart pumping any blood? No, it's not. It's not pumping any blood. So if your heart rate gets so fast that there's no fill time, it can't pump any blood. And so when your heart rate gets up around 300, there is zero fill time, none at all. So if your heart rate is at 300, it's not doing anything except sitting there and pumping so fast, it's called flutter. And flutter does not deliver any blood. And flutter often leads to fibrillation. Everybody remember what the ECG for fibrillation looked like? Remember, it doesn't have a P and a QRS and a T. It just looks like this. Make sense? Well, when we talk about fill time, David, we're really talking about the ventricle, but the answer is really and truly both, because they're connected to each other. Okay, so let's go back to what we were looking at. So remember, this is a cycle. Well, this person's heart rate is 75. And so look how much fill time they have. Here's the T wave right here, and here's the P wave right here. They have this much fill time. So look, we can divide this cycle up into different sections, and each section has a certain amount of time with it. Look, there's the P wave, there's QRS, and here is the T wave. So look, from P to QRS is 100 milliseconds. From QRS to T is 300, well, 275 milliseconds. But look, this is the rest of the time right here. That is the fill time. And so at a heart rate of fill time, if you have a heart rate of 75, we have this much fill time. But again, as the heart rate gets faster and faster, the amount of fill time is going to go down. Well, the heart is going through a cycle. And look what happened here. The atria contracted. So the atria contract, and they push the blood down here. And then the atria relax. They relax. And then the ventricles are going to contract. And the ventricles are going to push the blood in up this way. And then the ventricles are going to relax. And that's when we get fill time. And so there's a word that we use for contraction and relaxation. In the heart, we don't say contraction, we say systole. So systole is contraction. And in the heart, we don't say relaxation. We say diastole. So these are two words that you need to learn the meaning of, because we're going to use them over and over and over. So systole, contraction. Diastole, relaxation. Make sense? So when we go back and look at this again, look, there's that word, systole. Atrial systole. So what does this mean right here? What's happening? Atrial contraction, exactly. And then look, the atria are going to go into diastole. So there's where it starts, and it goes all the way to here. So what is atrial diastole? What does diastole mean? Atrial relaxation. And look, as soon as the atria start relaxing, look what happens to the ventricles. The ventricles go into systole, and they stay in systole to right here. And then the ventricles go into diastole, and they're going to stay into diastole until right here. So when we look at this cycle, we can see what's happening. Atrial systole, that's the contraction. Atrial diastole, that's the relaxation. Ventricular systole, that's the contraction. Ventricular diastole, that's the relaxation. So again, we need to learn those two words. Any questions so far? So here's another little pie chart. And look, again, average heart rate. Anybody remember what it is? 75. So how long does one beat take? How long does one cycle take? What is it? 0.8 seconds. What's another way of saying 0.8 seconds? 800 milliseconds, exactly. And so look, that's exactly what we see here. So here's where we're going to start. And look, 0.1, 0.3, 0.4, that's a total of 0.8 seconds or 800 milliseconds. And you can see what's going on. So here's atrial systole. Here's where the atria go into diastole, the ventricles go into systole, and then all the way back and start all over again. So it's a cycle, it's a circle. Well, there's a lot that goes on in a cardiac cycle. A lot of stuff happens. We've got this electricity going on. We've got the heart contracting, so we're going to increase and decrease pressures. We've got the blood coming into the heart, so it fills up. We've got the blood going out of the heart, so it empties out. It's a lot. And for a really long time, it was very, very difficult to picture all of this in your head because you had to imagine all this happening. Until around 1920, this guy right here, his name was Carl Wiggers. And Carl Wiggers taught at a med school. And what he decided to do was try to put all of that stuff we just talked about, pressures, volume, the ECG, heart sounds, all of that onto a single picture, a single diagram, so that you could see what was going on at any one point in time. And he came up with this, which is now called the Wiggers diagram. And here's what the Wiggers diagram looks like. So mine is in color, the one that you have on your screen, but I asked you to print a different one. And that one that you're printing is in black and white, but it's really exactly the same. But look at all this stuff that's on here. And so we're going to go through it a little bit at a time. And so what I'd like you to do is get out the Wiggers diagram, if you don't already have it out, and we're going to look at it. So your Wiggers diagram should look something like this. Is that the right one? I don't know. Well, anyway, should look something like that. Or there's a better one. Let's see. Well, I guess we'll just use our color one. But anyway, so let's look at the Wiggers diagram. So somewhere on your Wiggers diagram, you should have an ECG. Everybody find the ECG. Well, we already know what this is. Remember the P wave? That's where the SA node is going to begin to depolarize. The atria are going to depolarize. Here's QRS. The atria are going to repolarize, but the ventricles are going to depolarize. And then here's the ventricles repolarizing. Nothing new to that. Everybody remember it? So what is the P wave? Atrial what? Atrial depolarization, exactly. And then QRS, remember what that is? It's two things. What is it? It's the atria doing what? They're repolarizing, but at the same time, we can't see this because something else is happening. The ventricles are what? They're depolarizing. And then what is the T wave? Everybody remember that? What happens with the ventricles there? Ventricles are repolarizing. And then look, there's this long pause. And so during this long pause, remember that's the time between beats. That's our fill time right there. So, and then it's going to start all over again with another P wave. Look, ours lasts how long? 800 milliseconds. So if this cycle is lasting 800 milliseconds, what's the heart rate of this person? 75, exactly. So there's nothing new there at all. We didn't learn anything new. All it is our timer. That is just the time of the cycle. And then there's our ECG. But we know what's going on with the ECG. Remember, it's the electricity. And so P wave, atrial depolarization. Well, right behind depolarization, remember, the atria are going to contract. So right there is atrial systole. And then remember QRS, the atria are going to repolarize. So right there, the atria are going to go in to diastole. And they're going to stay in diastole all the way until we get to another P wave. Make sense? What does systole mean? Contraction. So the atria are going to contract. And then what does diastole mean? Relaxation. So the atria are going to relax. Well, remember, at the same time atria are going to relax, the ventricles are going to contract. So look, if we come down, here's where ventricular systole starts, right there. And then there's where it ends. So that's where the ventricles are going to go contract. They're going to go into systole. As soon as we get to the T wave, though, they're going to go into diastole. Well, remember, a good way to think about contraction is to think about squeezing. And in fact, think about squeezing a sponge. So you've got a sponge and it's got water in it. So I'm going to squeeze the sponge, and that's going to make the water come out because I'm going to increase the pressure and the water is going to squeezed out. So the P wave is, no. Remember, P wave and T wave are not contraction and relaxation. Let's go back. We go back to this. Remember, the P wave is depolarization. Contraction happens between depolarization and repolarization. It happens between these two. So here's the P wave, and there's QRS. So contraction happens between them. It happens here. Same thing here. Here's ventricular depolarization, and here's repolarization. Depolarization, repolarization. Contraction of the ventricles happens between these two. It happens here. So if we look on the ECG, here is where the atria contract, right here. And here is where the ventricles contract, right there. Does it make sense now? Well, we didn't change anything. Look, it's still PQRST. So right here is where the atria are going to contract. Right here are where the ventricles are going to contract. And so look, all we did was put that on there. There's atrial contraction right there. And there's ventricular contraction right there. Does that make sense now? So look, still nothing really new. Everybody got this part? So we got a timer. We got the ECG. We know about depolarization, repolarization. We know when the contraction happens. So there's when atrial contract. And then there's when the atria relax. There's when the ventricles contract. And there's where the ventricles relax. Make sense? So, again, you need to think about systole like squeezing. The heart is squeezing together. And when you squeeze something, you increase the pressure inside it. And so what we're going to see is an increase in pressure. So the next part of this Wiggers diagram is about pressure. So look, it's squeezing right here, squeezing in. And it's increasing the pressure on the blood. And that's what makes the blood move, is the pressure. Same thing here, when the atria contract, they squeeze in. That's what makes the blood move. And so when we look at this, here's the next part of our Wiggers diagram, and it's all about pressures. Remember, we measure pressure in millimeters of mercury. So there are 3 pressures we're going to look at. So this Wiggers diagram is only looking at the left side of the heart. So that means the left atrium, the left ventricle, and the aorta, which is the large artery that comes out of the left ventricle. Now we could put the right side on here too, but if we did that, we'd have 3 more lines. So we'd have another line like this, and another line like this, and another line like this. 3 more lines. It would get even more complicated. So to simplify it, we're only looking at which side? Which side? Left. And so there's 3 lines here. Look, 1, 2, 3. One of these is the left atrium. And in this picture, it's the blue one. It's this one. So look, here's the left atrium right there, the blue line. Well, look, it goes up a little bit, it goes down a little bit, it goes up, but it never gets very high. So the pressure in the left atrium is very low. Remember, we looked at the walls of the atria. The atria have very, very thin walls. And so they cannot produce much pressure at all. But when the atria go into systole, look, the pressure goes up. And when the atria go into diastole, the pressure goes down. So if we look at the pressure of the atria, remember it's only the left one, all the way through, It goes up during atrial systole, and it goes down during atrial diastole. Does it make sense? Well, look at what the maximum pressure is in the left atrium. I don't know. Let's see where it is. There's the maximum, probably right there. Look at what it is. What number is that? Maybe 13? No, not 25. 25 would be up here. That would be 25. You look at how the other thing is 30, 60, 90. So it's not even half of 30. Half of 30 is right there. So it's around that. So about 15 millimeters mercury. Really about 13. Does everybody see that? So it's not much pressure at all. No, David, this is the left side, not the right side. So David asked if it's part of the pulmonary circuit. After we do the left side, we'll come back and look at the right side, and you'll see how much lower it is. But pulmonary is the right side, not the left side. Okay, so atrial systole, we're going to get the squeezing a little bit. What's going to happen is the blood that's in the atrium, we're going to squeeze in. It's going to get pushed down into the ventricle. And then, look, we go to QRS. Well, remember what happens to the atria during the QRS is they relax. We're going to go into atrial diastole. So the pressure is going to fall. So the pressure falls. But also at QRS, the ventricles are going to contract. So we're going to go into ventricular systole. So let's see what happens with the ventricle pressure. That's this one. So the red line is the left ventricle pressure. Well, remember, the left ventricle is very thick walled, and so it can produce a lot of pressure. So when it goes into systole, look what happens to the pressure. It was down here. It's going to shoot up, and look how high it goes. It goes way up here to probably right along there, maybe about 125 or 120 or something like that. But the pressure is very, very high. Make sense? Well, again, think of this as squeezing. So in other words, when the ventricles start squeezing in like this, they're going to apply a lot of pressure to that blood, and it's going to force the blood out. It's going to force the blood into the aorta. Well, as soon as you force blood into the aorta, look what happens to aortic pressure. It goes up too. Now, it never goes exactly to 120. It might go to 119, but it can't go exactly as high as it is in the ventricle. It's just a tiny bit less. A tiny bit less than the ventricle pressure. But look, there it is right there. And so whatever that is, that's going to be the aortic pressure. But then we're going to get the T wave. And what are the ventricles going to do? They're going to go into diastole. What does diastole mean? It means to relax. So what happens to the squeezing? What happens to these ventricles when they go into diastole? They relax and they stop squeezing. So what happens to the pressure? The pressure falls. Does it make sense? Let's look at the aortic pressure right here. Look, the aortic pressure also falls, but it never falls down as low as the ventricle pressure. And that is because the aorta and large arteries have sort of like rubber bands in their walls. They're very elastic. Well, think about what happens if you take a rubber band, here's my rubber band, and I stretch it. Look, now it's this long. But look, as I stretched it, I added energy to it. I put potential energy in there. Well, aorta is the same way. So here's the left atrium, left ventricle, and here's the aorta. So when the ventricle pushes blood into that aorta, the walls are like rubber bands. They bulge out. Well, think about what happens to a rubber band. You stop pulling on it. What does it do? Because it's elastic, what does it do? It's going to go back to its original length. And that's what's going to happen here. When the ventricle stops pushing blood into the aorta, the walls of the aorta squeeze back in. They have recoil. And that recoil keeps the blood pressure from falling to zero like it does in the ventricle. It keeps this from happening in the aorta. So if we look at aortic pressure, it never gets quite as high as it does in the ventricle, and it certainly never goes as low as it does in the ventricle. And so that keeps the blood flowing even when in between beats. So that aortic pressure from the rubber band like things keeps blood flowing even when your heart is between beats. Does that make sense? So we've got 3 pressures. So what's the blue line? What pressure is that one? It's atrial pressure. What pressure is the red one? Ventricle pressure. What pressure is the black one? Aortic pressure. Exactly. So you can follow then what happens to the pressures in one beat. Look, remember, here's our P wave. There's the P wave. This is one cycle right here. So look what happens. We're going to get the P wave. Atria are going to contract, and we're going to go into systole, and the pressure is going to go up a little bit. Blood's going to get pushed down into the ventricles. And then the atria are going to relax. We're going to go into diastole, and the ventricles are going to contract, and pressure is going to go up, way up to about 120 until the ventricles begin to relax. And it's going to come back down. As this pressure goes up, it's going to force blood into the aorta. And so aortic pressure is going to go up until the ventricles begin to relax, and then it's going to fall. But because of these elastic fibers in the walls of the aorta, those elastic fibers prevent it from falling down to zero. And then it's going to happen all over again. Make sense? Any questions? So here's another thing. Remember, we have valves in the heart. Everybody remember? We're only looking at the left side again. Remember, there's going to be the left AV valve right here. And there's going to be the aortic semilunar valve right here. Everybody remember that? Remember the valves open and close due to pressure differentials. Pressure differentials. So look what happens. Everywhere these lines cross, everywhere the lines cross, the valve is going to do something. So if we look at this first, look over here. Where is the pressure higher? If we look over here, where is the pressure higher? Is it higher in the atrium or is it higher in the ventricle? Look over here. Which line is higher, the atrium or the ventricle? Look at it. The blue line is above the red line, right? So the pressure is higher in the atrium than it is in the ventricle. The pressure is higher in here than it is in the ventricle, and it's going to push this valve open. Blood's going to flow in here. But look what happens right here. That red line goes higher than the blue line. So now, where's the pressure higher? In the atrium or the ventricle? Right there and above. Where's which one? What's higher now? Which one's above, the red or the blue? Starting right there. So look, now the pressure's higher in here. So it's going to squeeze in. And this valve was hanging down like this. But as soon as the blood tries to go backwards, this valve's going to close. So right there, where those two pressures switch, the left AV valve closes. Does that make sense? Again, they open and close due to pressure differentials. Over here, the pressure's higher in the atrium. And so the valve is open. Blood's going this way. But the second you get right there and over here, the pressure's higher in the ventricle. And so the blood tries to go backwards. And so the valve closes. So right there, where these lines cross, that's where the left AV valve closes. That bicuspid, that mitral valve closes right there. Does it make sense? Let's go back over here. So let's look at the aorta and the ventricle. So right now, all over here, which line is higher, the aorta or the ventricle? Where's the pressure higher? Pressure in the aorta is like 90 or a little bit below. But look what it is in the ventricle. It's like 0. So right there, I'm not doing a very good job of drawing. So the pressure is higher here. So that means this valve is closed. So this valve is closed all the way. But look what happens when we get right there. That means the ventricle is squeezing in. And above that, look who's ahead now, or look who's higher now. Is it the red line or the black line? Is it the ventricle or the aorta? And so when the ventricle pressure gets higher, what's going to happen is the valve is going to open and blood's going to go this way. So right there, that valve, the aortic valve, is going to open. right where the lines cross. So here, the left AV valve closes. Here, the aortic valve opens. Does it make sense? But let's follow it on over here. So over here, all the way, the aortic valve is open because the ventricle pressure is higher. But look what happened right there. Now who's higher? The aortic pressure or the ventricle pressure? So as soon as the ventricle pressure falls below the aortic pressure, this valve, blood's going to try to go backwards. This valve is going to close. So right there, the aortic valve is going to close. Right where those lines cross.
Motion detected at the front door.
I'm sorry, the garbage people are going by. And then look, if you keep following, look, aortic pressure, higher, ventricle pressure is here, ventricle pressure keeps falling. But look what happens right there. Now, which pressure is higher? The ventricle pressure or the atrial pressure? Which one's higher? And so as soon as that happens, that means that the pressure in the atria are now higher than they are in the ventricles. And so the pressure this way is higher. So this valve is going to open back up and blood's going to go this way. So what we see are 4 places. Every time these lines cross, a valve either opens or closes. So here, the left AV valve closes. Here, the aortic valve opens. Here, the aortic valve closes. And here, the left AV valve opens back up again. Does it make sense? Again, all you have to do to figure out if the valve is open or closed is remember the orientation of the valve. If you remember the orientation of the AV valve, it's like this. Think of it like a trap door. So if the pressure's higher here, it opens. But if the pressure's higher here, it's going to push this way and push this way, and it's going to close. Same thing is true for the SL valves. But remember, the SL valves are oriented like this. So if the pressure's higher here, they're closed. But the pressure higher here, again, it's like a trap door. They're going to open. So, one more time. Look at who's higher here. Who's higher, atria or ventricle? Right here. Who has more pressure? The atrium. So, right here, the valve is open. But, right here where the lines close, now who has more pressure? The ventricle. As soon as that happens, the valve is going to close. Look here, who has more pressure, the aorta or the ventricle? Who has more pressure, aorta or ventricle? The aorta has more pressure. So here the valve is closed. But look what happens right there where the lines cross. Now who has more pressure? And so that's where the valve is going to open. And it's going to stay open until here. Now who has more pressure? The aorta or the ventricle? There's the aorta. There's the ventricle. Who has more pressure? The aorta. So as soon as this pressure here drops, the valve is going to close. And then if you follow it, it keeps going down. Right here, who has more pressure, the ventricle or the atrium? Ventricle has a whole lot more pressure until we get to right there. And then when you get to right there, who has more pressure, ventricle or atrium? And so the left AV valve opens back up. Everybody got this? Any questions? There's one more little thing right here, and that is this thing right here. It looks like a big bump, jump up, sort of. It's called the dicrotic notch. So the dicrotic notch is this little thing right here where you have this dip and then a jump back up. So think about this. If I were to just run and just throw myself at a wall, I'm going to run and hit this wall. Would I stick to the wall? What would happen to me if I just ran into the wall besides getting hurt? What would happen? Would I stick to the wall? Yeah, I would bounce back is what would happen, right? Well, that's what happens here. When this valve closes, the blood bounces back. And for just a tiny bit of time, that bounce makes the blood pressure jump up just a little bit. So that bounce in blood pressure is due to the closing of the valve. So that's all that's on this part. So let's review again. So again, there's our timeline. That's all it is. Remember, this has a heart rate of 75 beats a minute. So how long does one beat last? 800 milliseconds, and then it's going to start over again. There's our ECG. We already know what happens at all those different parts of the ECG, the P wave, the QRS, the T, the pause, P, QRS, T, pause. Remember what's going to happen? After the P wave, the atria are going to contract, and then QRS, after that, the atria are going to relax. QRS, the atria are going to, or the ventricles are going to contract, and then after the T, they're going to relax. Well, again, you need to think of this contraction, this systole, like squeezing. And what you're squeezing is the blood. And so if you're going to squeeze, pressures are going to go up. And so while this is squeezing, pressure goes up. Now, it doesn't go up much because they're very, very, very thin wall. Not much muscle at all. But it goes up a little. When the ventricles contract, though, remember this left ventricle is very thick. That pressure goes way up. When it relaxes, it comes back down. So, systole, squeezing. So squeeze, the pressure goes up. Diastole, relaxing, pressure comes back down. And then the third pressure is this pressure in the aorta. So That's caused by the blood that's in the aorta. There's blood in there. So when we force more blood into the aorta from the ventricle, we force more blood in there, the pressure is going to go up. When we stop forcing it, it's going to go down. But remember, the walls of the aorta have like little rubber bands in them. So when the ventricle pushes blood in there, they bulge out. The walls stretch and they absorb some of the pressure. It's like pulling a rubber band. And then when you let go of a rubber band, it goes back to its original shape. It has recoil. And so when the ventricle stops pushing blood, it goes back to its original length. And that, again, is pushing against the blood. So even though the pressure falls, it doesn't fall like it does in the ventricle. So if we look at the pressure in the ventricle, it goes up to about 120, and it falls all the way down to about 0. Look, it falls down to almost 0. But if we look at the pressure in the aorta, it goes up, but it never drops down to 0. It only goes down to about 80. Does it make sense to everyone? Any questions? Okay, well, there's one more thing on the Wiggers diagram, and that is the amount of blood. The amount of blood in the ventricle. So we're not talking about pressure anymore. What we're talking about here is volume. Look, it's in milliliters. So look, the ventricle fills up and then it empties out. It fills up and then it empties out. Remember, it's squeezing. So look, when the atria contract, they force blood into the ventricle. Blood volume goes up. When the ventricles contract, they force blood out of the ventricle, and so it goes down. So this is the volume of blood in the ventricle. In other words, how full is the ventricle? Well, remember, over here, this valve is open. So whatever blood comes into the atria just goes on down into the ventricle. So it goes up. And then right here, we're going to get systole. So the ventricle or the atria are going to contract. And whatever blood is left in here is going to get pushed down into the ventricle. And then the ventricles are going to contract. So when the ventricle starts contracting, it squeezes in. This valve's going to close. This valve's going to open. And it keeps squeezing in, and blood is going to get forced into the aorta. So ventricle volume is going to go down. Makes sense? So all this is the ventricle filling up, the ventricle emptying out, the ventricle filling up, the ventricle emptying out. That's all it is. Make sense? Well, if you look at this, there's two volumes here. One is the volume at the very end of diastole. Remember, diastole means relaxation. So in other words, at the very end of relaxation, right before the heart contracts, that's how full the ventricle is. It's called the end diastolic volume, or the EDV, end diastolic volume. That's as full as the heart is going to get. That's as full as it's going to get. So how full did this person's heart get during this beat? What was the fullest that the heart, the ventricle was? It was that amount. Does that make sense? So what is that amount? It is the EDV. Make sense? And then the heart's going to squeeze. It's going to squeeze the blood out of the ventricle and into the aorta. So as soon as this valve opens and blood starts going into the aorta, look, the volume's going to go down. And if we follow this volume, look, it's going to go down, go down, go down, go down. And that's as far down as it's going to go. That's at the end of systole. It's the end systolic volume. And that's as empty as the heart is going to get. So is the end systolic volume, is it 0? Did all of the blood get pushed out of the heart? No. There's still this much left in the heart. And so if you start exercising and I squeeze harder, because you can do that, if you squeeze harder, then this number will go down even lower. But we have this much blood left in the heart at the end of every beat that we can use if needed. If you start exercising, you need more blood to move. And so your heart pumps harder. And so our ESV will go down. But there's two numbers here that are important. The EDV and the ESV. What is EV again? The end diastolic volume. That's as full as the heart is going to get. And what is ESV? That's the end systolic volume. That's as empty as it's going to get with this beat. So how much blood came out of the heart? We can figure that out. All we have to do is subtract EDV minus ESV. That's how much came out. And there's a name for that too. It's called the stroke volume. The stroke volume. So what is the stroke volume for this person, for this beat? What is this stroke volume? We just take 130 and subtract what from it? 50. And so we get 80. So that means that with this beat, this person pushed out 80 millimeters of blood. Does it make sense? Guys, don't click on my PowerPoints because you'll change everything. Any questions? So that's the Wiggers diagram. So if we go back through it real quick, remember first all we had was this timing mechanism. We used that. We used our ECG. Remember what ECG means. P wave, atrial depolarization. QRS, atrial repolarization. T wave, ventricular repolarization. And remember, right behind atrial depolarization, we're going to get atrial systole. Right behind ventricular depolarization, we're going to get ventricular systole. And then they're going to relax. During systole, remember, we're going to create pressures. And so if we look at the pressures, there's three pressures. There's the atrial pressure, ventricular pressure, and aortic pressure. So when the atria are in systole, atrial pressure goes up. When the atria are in diastole, atrial pressure goes down. When the ventricular systole, ventricular pressure goes up. Ventricular diastole, ventricular pressure goes down. And then when the ventricle pushes blood to the aorta, aortic pressure goes up. And when the ventricle stops pushing blood into the aorta, aortic pressure goes down. But remember, the walls of the aorta are like rubber bands. They bulge out. And so they store some of this pressure. And so when the heart relaxes, that squeezes back in. And so aortic pressure never falls down as low as ventricular pressure. And then we have these valves. And the valves open and close with pressure differentials. So where these lines cross, right where the lines cross, that's where the valves are going to open and close. So the lines crossed right there. Over here, the blue one was higher. But over here, the red one is higher. Right here, the lines cross. Over here, the black one is higher. But over here, the red one is higher. Same thing over here. Does it make sense? It's where the lines cross. And then the last part is the volume. So when the ventricles contract, volume goes down. When the ventricles relax, volume goes up. And then the two volumes that are really important are these two volumes, EDV and ESV. And if you subtract those two, you get the stroke volume, or the SV. Does it make sense? So look, here's another picture, same thing. So there's our P wave right there. There's our QRS right there. There's the T wave right there. So if we look at that, P wave, atria depolarize. Right behind that, the atria are going to contract. So atrial pressure is going to go up. And then we get to QRS. Atria are going to go into diastole. So atrial pressure is going to fall. But at the same time, the ventricles are going to contract. And when the ventricles contract, the pressure is going to go up, and it's going to go way up. It goes up to about 120. Well, as soon as the pressure gets higher in the ventricle than it is in the aorta, blood's going to enter the aorta, and aortic pressure is going to go up. And then the ventricles are going to relax. Ventricular pressure is going to fall, and then aortic pressure is going to fall, but it never falls as low as it does in the ventricle. And then if you look at the blood, look, the atria are full. That's where they're, and then these valves are open, so the blood just goes on down into the ventricles. And then the atria contract, And if there's any blood left in the atria, it gets forced into the ventricles. And then the ventricles contract. These valves are going to close. Blood pressure keeps going up. Finally, these valves are going to open and blood is going to leave the ventricle and enter the aorta. So if you put those two together, it kind of looks like this. So I hope that you can bounce back and forth between these two and tell what's going on. Does it make sense? Here's just another way of looking at it. This is just written out. So remember, this is a circle, a cycle. We can start anywhere we want to. Now, usually most people start here with the P wave, but you don't have to. And so when I wrote it out, I didn't start there. I started here. I started the T wave. So look, this is this quiet period. This is the period when everything is relaxed. This is the period when the heart is filling. And it's actually the longest part of the cycle. And so when I looked at this, that's where I started, the end of the T wave, this quiet period. And what's happening here is the heart is filling up. And then here it tells you what the valves are. And then here, next thing is going to be the P wave. So we're going to have the P wave. We're going to get atrial depolarization, atrial systole. Whatever blood is left in the ventricles or the atria are going to get pushed down into the ventricles. Here's what the valves are doing. And that's this period right here. That's this period right here. And then we're going to have QRS. Sorry, then we're going to have the T wave. No, QRS, I was right. QRS, and so the ventricles are going to depolarize, the atria repolarize. That's this period right here. This period right here. And then finally, we're going to get back to the T wave again. There's our little dichrotic notch. Remember, bouncing backwards. And then back to the T wave. And then it starts all over again. So if you learn one cycle, you've learned them all because they're all identical. They all do the same thing. One cycle, and it starts all over again. Then another starts all over again. This is not a very good picture here, but this shows you what's going on. It's a little too busy though. But anyway, if you see it in class, it's not quite as busy. And this is a GIF is what it is. And so it changes all the way through here and all the way through here. But it doesn't show up that way. Yeah, this is the stuff that's on the lecture exam. Okay, well, when we looked at this, remember we were only looking at the left. Left atrium, left ventricle, aorta, just the left. We could look at the right, and if we did, we'd have to put 3 more lines on here. And so it gets really, really, really busy. So if you want to look at the right, it's actually better to do it by itself. So here's the right over here. So look, here's the right atrium, the right ventricle, and the pulmonary artery. Well, look at these numbers. Here's my left one over here, the one we just looked at. Remember, there's the atrium. There's the atrium. Not much different. Ventricles, though, look how different this is. That's the left ventricle. Here's the right ventricle. If we look at it, the pressures are very different. This is 120. Look at what this is. It's about 40. In fact, everything on the right side is lower because the right side of the heart is not nearly as thick. Yeah, you'll never see these two on the same graph. It's just too many lines. So yes, it would look like this. But there's one thing on this two graphs. Everybody look at them. This is different from that. This is different from that. This is different from that. Everything is different except one thing. And the one thing that is not different is this. It's exactly the same. In other words, exactly the same amount of blood goes through both the right and the left sides. Exactly the same amount. In fact, the heart must pump the same amount on both sides, the exact same amount. If it doesn't, you get a disease, and the disease is called congestive heart failure. So congestive heart failure is when one side is pumping more than the other side. These two are not exactly the same. Congestive heart failure is when one side is failing. And depending on which side it is, you get very different symptoms. If it's the left side that's failing, you tend to get pneumonia. If it's the right side that's failing, you tend to get peripheral edema. Your arms and legs and feet swell up like crazy. So in other words, there's fluid backing up behind the pump. It's either backing up in the lungs or it's backing up in your peripheral tissues. So you probably have heard of people with heart disease and they have problems with pneumonia. Or you probably have heard of people with heart disease whose hands and feet and legs and so on swell up like crazy. Again, that's called congestive heart failure. And it's when one side is pumping more than the other side. One side is failing. Any questions about the Wiggers diagram for either the left side or the right side? Once you learn it over here, you should be able to just interpret it over here because it's not any different. It's just the lines are lower. But just like we have atrium, left atrium over here, we have right atrium over here. Just like we have left ventricle over here, we have left ventricle over here. Just we have the aorta over here, we have the pulmonary artery over here. And then again, just like we have volume over here, we have volume over there. Does it make sense? Any questions? Well, remember we already talked about this, but when the heart valves close, it's like closing a door, and you can hear it. And so these are the heart sounds that we hear. So when this valve closes, you hear the first heart sound. And when this valve closes, you hear the second heart sound. And remember, the heart sounds a little bit like lubbed up. So first sound, AV valves. Second sound, SL valves. Now, just like you can also hear doors open, you can hear the valves open too. But those those sounds are very, very minimal compared to the others. So unless you have a really, really good device, you would not hear these sounds at all. But if you want to hear the sounds, we use a stethoscope. But if you've ever been to the doctor and noticed what they do when they listen to your heart, they move the stethoscope around. Well, they don't move it randomly. They move it to very, very specific spots. And each of these spots is where you can hear particular valve the best. And so what they're listening for when they listen is they're listening to see if these sounds are nice, clear, crisp sounds, or if there's something weird about the sound. So remember, the heart is supposed to sound like bloop, 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 bloop. But if you listen and you don't hear that, you hear like whoosh, whoosh, some sort of swishing sound, or some sort of really elongated sound. That means that the valves are leaking. I don't know if you ever did this when you were a kid, but you can even do it now. If you take a balloon and you blow up the balloon, and then you let the air out just a little at a time. When the air comes out, the balloon vibrates and it squeals. You can hear it. If you have a balloon at home, try it. It makes a really high-pitched squealing sound. Well, when the blood goes through the valve, and the valve is supposed to be closed, but it's just got a little opening, it's leaking, you can hear that sound. It makes this high-pitched swishing sound. Make sense? Any questions? Okay, so I think that's probably enough to cover for today. So what I want you to do is, if you've already, if you printed this thing out, if you look at it over to the side, there's going to be little leader lines. So you'll have a little leader line right there, and it's got like the letter A next to it. And then there'll be a little leader line right there, and it'll have like the letter B, and then same thing here. All the way it goes A, B, C, D, all the way down to like, I don't know, L or M. Well, whatever that letter is going to match up with one of these things. So you need to figure out what A represents. So let's practice. So if this is A, so over here, what does A represent? What is A? You remember? Aortic pressure, right? So if this is B, what does B represent? B is ventricular pressure. Make sense? You're also going to see a leader line right here. So I don't know what it is. Let's say it's J. What does J represent? Remember, it's where these lines cross. It's where this happens. And then, remember, we have this. That's the ventricular volume. But we also have this. And this, remember, in diastolic volume, in systolic volume, stroke volume. So what you need to do is just make it, fill out what these letters mean and practice with it. Again, that one that I gave you to print has leader lines. I don't have that one showing, but it looks similar to this one. And then don't forget to go over this. So this, remember, is a cycle. It's a circle. It just happens over and over again. Remember, there's P wave, there's QRS, there's T wave. This is what happens here. This is what happens here. This is what happens here. Remember, this is that period of filling. It's the fill time. And then it starts all over again. Also remember, a typical heart rate, average heart rate, 75 beats per minute. And if the heart rate is 75 beats a minute, then one beat takes 0.8 seconds or 800 milliseconds. Is there anything on the Wiggers diagram that you don't get or don't understand? So the value in this Wiggers diagram is that it lets us see everything that's going on in the heart in one picture, in one view. We can see everything that's happening. We can see when systole happens, when diastole happens. We can see when the valves open and when the valves close. We can see the pressures going up and the pressures coming down. We can see the volume going up and the volume coming down. We can see all of that in one picture. Any questions? So I'm going to stop there, and then next time we're going to talk about cardiac output, and that'll be the last material for the exam. So once we finish this, we will have finished all of the material for the first lecture exam. I'm going to do it on Wednesday. So tomorrow, if you come back, it'll just kind of be a little bit of a repeat of this. I'll answer questions and run back through this again. But remember, new stuff is on Mondays and Wednesdays. The other days is Q&A is what it is. So this will be on Wednesday. I'll also post this on eCampus and also on the YouTube. So if you want to re-listen or re-watch it, you can always go back through the recordings. Any questions? Okay, well, my other class is about to start, so I need to go ahead and go. But again, I'll see you on Wednesday. And for those of you who tried to take the endocrine disorders quiz and we're having problems, I think those problems have been fixed. So I just deleted the scores that you had because there were just too many missing pictures or whatever. And so go in and do it again, and then you should be able to. If you can't see it, let me know, but I think I fixed everything. Okay, well, have a good afternoon, and I'll see you on tomorrow if you come tomorrow.